we're going to look at the 2011 AP Statistics exam. This is problem 1 from the free response section. We'll do this question quickly, and then we'll also move on and do problem 2 as well. Let's take a look at it. It says a professional sports team evaluates potential players for a certain position based on 2 main characteristics. And they seem to care about here speed and strength. Speed is measured by the time it takes to run a distance of 40 yards, with smaller times indicating more desirable, faster speed. Still always something to keep in mind with statistics. Generally, smaller numbers are faster and better, and it happens on a lot of problems, actually. So what do we know here? They tell us that from previous speed data, we look at the next sentence there, starting right here. For all players in this position, the times to run 40 yards have a mean of 4.6. So I'm going to write mu equals 4.6. And a standard deviation of 0.15 with a minimum time of 4.4. So the min, here's the min they're telling us. Okay, so notice they don't mention the word normality here. I was looking for the word normality because then if I can make a z-score out of it, I can use normal CDF, but it doesn't say anything there. Let's see what the question's asking. Based on a relationship between mean, standard deviation, and minimum, is it reasonable to believe that this distribution of 40-yard running times is approximately normal? Well, let's do a little bit of calculations here. Let's see the z-score that goes with 4.4. Keep in mind, this is the mean, this is the standard deviation. So to get a z-score, z equals x, your observation that is, minus your mean over your standard deviation, which in our case, we're going to find the z-score for the minimum. There's the mean. There's the standard deviation. So it's going to be 4.4 minus 4.6 over 0.15. And if we take a minute to do that, we get, hold on here, negative 1.33. So if this were going to be a normal standard deviation, or a normal distribution that is, sorry, then the mean of 4.6 would be in the middle. And our minimum in this distribution, according to the problem, was 4.4. So here's where the problem lies. 4.4 isn't even 2 standard deviations away from the mean. It's only right here. It's at z equals negative 1.33. It is negative 1.33 standard deviations below the mean, which means there's still a considerable amount of area here that should be accounted for. If we want, we could find it. We could say second distribution is normal CDF. Lower number is some really, really negative number. Upper, I'll do that z-score of negative 1.33333. I'll leave the mean in 0 and standard deviation at 1. And we get an area of like 9%. So this is one way to say that this distribution probably is not normal. Because if our minimum is 4.4, then we would have expected 0.09 of the area to be below that, or about almost 10% of the area, if this were indeed, in fact, a normal distribution. So the question is, do you think it's normal? Your answer should be no, I don't think it's normal, because if it were, then this minimum of 4.4 should have had almost no area below it. So maybe if it was like negative 3 standard deviations below the mean, or negative 4, then we might say, you know, it could be normal, possibly. But this, I think, because 10%, almost 10% of our area is still below this number, then the real distribution is probably not normal. It's probably skewed right. Okay, let's see what it says next. So part B of the question, strength is measured by the amount of weight lifted, with more weight indicating more desirable strength. So here we're going to calculate a z-score for this person. That's what all are asking, calculate and interpret the z-score. So to get a z-score, just like we did before, z equals the observation, which in this case is 370 pounds, which sounds impressive, minus the mean of 310 over the standard deviation of 25. So 370 minus 310 gives you 60, and then we divide by 25, and we get a z-score, a z of 2.4. So the question also is, how do you interpret this? Make sure you show the calculation of the z-score. You show this thing over here. The interpretation is this. Z-scores always give you the number of standard deviations you are away from the mean. In this case, since Z-score is a positive number, you notice we have it's not, I didn't write it here, but it's a positive 2.4. It means that this person's, let's say their their lifting of weights of 370 pounds is 2.4 standard deviations above the mean. So this person's, you know, pretty strong compared, or in a relative way, we'll say. Okay, so finally, the characteristics of speed and strength are considered to be of equal importance to a team when selecting a player for the position. Based on information about mean and standard deviations in the problem above, we have two players A and B, and we have to make some kind of justification for picking one of them. All right, so I think the whole problem is about Z-score and seeing how they compare. Let's find our Z-scores for each player. So for player A, we're going to do the Z-score for their running time, and then for player B, we'll do the Z-score for their running time. So just remember the mean running times, just in case we forget them. Here they are. The mean running time is 4.6 seconds, and the standard deviation is 0.15. So the Z-score here is going to be 4.42 minus 4.6 over 0.15. And for this person, it's going to be 4.57 minus 4.6 over 0.15. So let's calculate them both here and see what we have. That first Z-score, wait for it, sorry, divided by 0.15, we are getting a Z-score of negative 1.2. Now keep in mind, it's good to have a negative Z-score when we're talking about running times, because this person is faster than the normal person, or the mean person, we'll say. Let's do the other person's Z-score, 4.57. This will not be as negative of a number. And when we divide this, we just get negative 0.2. So what we can say is, in terms of speed, person A is faster in a relative way. Okay, so now let's look at the strength. If you look at player B looks pretty strong, right? And player A looks reasonably strong. We need Z-scores for that. So Z is going to equal the observation of 370 minus the mean over the standard deviation. Let's just remind ourselves of those things. For the weightlifting, the mean is 310 and the standard deviation is 25. So this is going to be 310 and 25. So we calculated this before, and yep, what was it? It was 2.4 standard deviations above the mean. Now this person's Z-score is obviously going to be higher. In the case of strength, we care about that, right? Because this person's stronger when the numbers are higher, if they can lift more. All right, so we find this person's Z-score, we end up getting is indeed a higher Z-score of 2.6. So then the question is to pick between these two players. Well, I guess you could make this argument. Here's what I would say. I would say in terms of strength, they're both more than 2 standard deviations above the mean, 2.4 versus 2.6. But in the case of the running times, person A, this person is 1.2 standard deviations below the mean, while this person's basically at the mean. Negative 0.2 is very close to Z equals 0. So what I would probably argue is that you could argue that these players are of equal strength, but person A is significantly faster than person B. And that would be enough reasoning because you've talked about Z-scores. A mistake that a kid could make here on the AP exam is they could actually take these Z-scores and go use normal CDF and try and use a normal distribution, which we know we can't do because we weren't told the distribution is normal. Okay, so that's it for that problem. What I'd like to do now is move on to problem 2 from the same exam. Let's take a look at this. Problem 2, the table below gives the political party registration by gender of all 500 voters in this Franklin Township. So when I look at a problem like this, I always like to look at a number maybe and see if I can tell what that means. So this number I circled in green means that there are 120 females that are consider themselves registered in Party X in all of the Franklin Township registered vote. Well, of all 500 registered voters. That's what that means. Okay, let's look at the blue number. Look at just this blue number here, 244. That doesn't take gender into account. That's the sum of the males and the females together. So that's just telling us there's 244 people in Franklin Township who are members of Party X. That's how that works. Okay, good enough. Let's get on to the questions. So, question A says, given that a randomly selected voter is male, what's the probability he is registered for Party Y? So look for that word given. Whenever you see that word given, that means you have a conditional probability. And so the notation for that is as follows. Given they're male, so you know probability, open parenthesis, vertical line, close parenthesis. Whatever is given goes after that vertical line. That's just how we write it. It's the convention. And then they say, what is the probability that he is registered for Party Y? So we're saying, what's the probability someone's Party Y given they're male? So there's really a couple ways to look at it. In this case, what I would think of is just we're only looking at the males. So if we only look at the male row, there they are, right? Got it? So I erased, I didn't circle that so well. But what you can see here is if we're out of just the males, we know our denominator, for example, is going to be 200. And then we know our numerator is going to be just the people who are in Party Y who are male. So that's 48. So you can leave it that way. If you want to divide it, you can. You should get about, yep, well, exactly, actually, 24% or 0.24. That's the answer to part A. If you want, there is a formula for conditional probability, and it says the probability of Party Y given male is equal to the probability of Party Y and male over probability of male. So if you were to use that formula in this question, it would work just fine. So when we go to do this numerator, for example, probability of Party Y and male, that number is 48 out of 500. So let's put that here. It's going to be 48 out of 500. And then the probability of being male, which I'm underlining in purple, the males in the study, that's 200 out of 500. You can see those numbers right there. So in the denominator, we put 200 out of 500. And what you should notice is you've got these 500s that cancel. And when you know it, you get the same exact number, 48 out of 200, or 0.24. So I'll leave it up to you how you want to do that problem. Okay, while we're at it, let's make a copy of this question because it's definitely getting crowded. And let's paste it here and try and write a little bit more. Okay, this is part B we're looking at now. Sorry about that. Let's get my pen. Here we go. All right, so it says, among registered voters of Franklin Townships, are the events is male and is registered for Party Y independent? And then they want your answer based on some kind of calculate, some kind of probabilities. So when you want to test for independence, there's two ways to do that. So they're testing, let's be clear here, is male and Party Y. So we're asking the question, are male and Party Y independent? Okay, there's two ways to do that. One thing you could say is, does the probability of being in Party Y given your male equal just the probability of being in Party Y? So that's one way to do it. Or the second way is, does the probability of being in Party Y and being male equal the probability of being in Party Y times the probability of being male? So I said in a previous video that I always, when I first started doing these independence problems, I always kind of like to do this way first, with this second method. I thought it was easy. You can just look in the table. So let's do that actually. Let's do it that way and then see what happens. So for this one, probability of Party Y and male, we look here, Party Y and male is 48 out of 500. That's what that's saying. So because this 48 I circled here is the number of males who are in Party Y, and then it's out of the total. So what I'll do there, I'll go down here. I'll put 48 over 500. Okay, then I'm going to need probability of being in party Y and probability of just being male. So let's look at the table for that. So probability of being party Y is 168 out of 500. And while we're at it, the probability of being male is 200 out of 500. Okay, so let's go put those numbers in. So this first number here, oops, sorry about that. This is going to be 168 out of 500 because that's how many voter people who were in party Y who were voters in this township. And then there were 200 males out of 500 males. Okay, so our goal now is to find out, are these things equal? So let's do a little bit of calculations. This turns out to be 0.336, and then we're going to multiply that by, that's 0.4, so times 0.4, gives us 0.1344. Over here, we already know that 48 divided by 500 is 0.24. So these things are not equal, which means you can say they're not independent if you want, or you can say these events are dependent. Okay, let's talk about checking it the other way. So this is sort of neat. The problem sort of led you in this direction if you think about it. This probability was asked about in part A. So we actually did that probability. Let's go back and find it. Here it was. Probability of party Y given male was 0.24. Yep, that's what it is. So we go back here. This is 0.24. And I'm realizing now I made a small error. Oh no, I didn't. This one here, I made a small error. I'll show you what I did before. Sorry about that. This number here, when I divided, I made a mistake. So let's just divide that again. 48 divided by 500. Yep, that's my bad. Sorry, this should have been 0.096. Okay, glad I fixed that. It doesn't matter though. These things are still dependent. They still didn't equal each other, so it's okay. I think I saw this 500 on the bottom. Was thinking of 200. Up here, that's what we have. So this was the answer from this little 0.24 was the answer from part A. And you should know the EP exam grades like in a wrong but consistent fashion. So if you had A wrong but used it correctly to make this decision, you'd still get credit. This is saying what's the probability the person's in party Y. So if we look at party Y, where are they? So that's these red circles here. There's 168 people in party Y out of 500 people in total. So we'll put 168 over 500. Let's divide that and see what we get. 168 divided by 500. And we get 0.336. Okay, so like I said earlier, I used to use method 2 much more often, but now I seem to favor this method, method 1. And my reason for that is I like the intuitive meaning here. This probability on the left-hand side is saying, what's the probability someone's in party Y, given we know that they're a male? And in that case, we get 24%. That's lower than just knowing the probability someone's in party Y without paying attention to gender, which is 0.336. So in other words, knowing a person was male made them less likely to be part of party Y. Hence, these two variables are dependent, or we could say they're not independent. That's it. Okay, let's take a look at the last part of this question and see what it has to say. There's a couple of things here. First off, they present us with this nice graph that we should look at. So if we take a look at it, part C starts off like this. They say to us, one way to display the table is the data tables use a segmented bar graph, which is pretty popular when you first learn about two-way tables. The following segmented bar graph, constructed from the data and party registration from Franklin Township table, shows party registration for males and females. So clearly you can see here, for example, we look at males, we can tell that most of them are in party X, and females seem to like party X and party Y equally, and then party W is sort of their least favorite. Okay, so this is just called a segmented bar graph, and we can see what it's telling us. question goes on to ask, what if all the proportions of registered voters for the parties, W, X, Y, were the same, right? And party registration was independent of gender? Then what would your graph look like? So if gender didn't matter, then we would expect the proportion of males and females that were favoring each party to be the same. So we can find that actually right at the bottom of the table. Let's just erase a little bit. I got a little bit of chaos going on here. Here we go. Let's get rid of that. So if we just pay attention to these numbers, for example, there's 88 people who like party W out of 500. So that should be our proportion then for both genders. So I'm just going to do 88 divided by 500. And if we do that, 88 divided by 500, we get 0.176. So we should expect in both cases that the segmented bar graph goes up to wherever you think 0.176 is. And since it's independent of gender, you should expect these segments to all have equal areas. Let's go looking for the next one. So I'll circle this in green. For party X, it should be 244 out of 500. So if I divide that for you, I'm getting 0.488. So you could say it's 244 out of 500 was 0.488. If I add that on to the 0.176, we get around 0.664. So it's going to end up out here somewhere. And without losing track, I think that was party X. Yeah, we were party X just now. So this is party X. Oh no, sorry about that. Yeah, it's party X. I mislabeled the first one. So these purple ones. All right, so that's my second mistake. I need you to be forgiving. It's party W. Okay, and then lastly, I think that last party was called party Y. It was. So this is party Y out here. If you wanted the proportion, you could actually divide them. You can go over here and take the 168 and divide it by 500. And you get the 0.336 that has come up a few times in this problem. The main idea of this part of the question is just to realize that if we have independence with respect to gender, then the segmented bar graphs for both genders should be the same. Okay, so that's it. Questions 1 and 2 from the 2011 AP Statistics exam. Thanks for watching.